Yes, thanks very much. So I realized that I didn't get as far as I wanted to yesterday. And so we have quite a bit of mileage to go. So I thought that we'd warm up, mathematically, of course. So we warm up, and because I also felt bad that I forgot about the transpose yesterday, so let's do that computation again, but this time with the factors correct. So a little warm up one. So I was told actually that one should warm up in the morning before you do mathematics, solve some integral or something. So let's take this submersion that we had from last time, u twiddle. So that's the submersion. And then I check the factors. So apparently the pullback map, which goes from C non infinity u twiddle to C infinity u, is given by the following kernel. So I of x comma y equal to 1 over 2 pi to the power n. Integral over Rn, and then we have e to the I theta. And now it turns out that it's very helpful to actually not write dot, but put an inner product there. Y minus f of x e theta. And notice that there is a 1 here that I didn't write down, but now I have, which is a symbol of order 0. So 1 is a symbol of order 0, of course. So this means m must be equal to minus n plus n twiddle. So n twiddle is the dimension of u twiddle, minus 2n divided by 4. So little n is the capital N here, right? So remember that formula, there was this shift. So therefore, the actual order of the operator gets a shift. If n is equal to n twiddle, then this is 0. So we have an operator of order 0, but if we map between different spaces, there is a shift in the order of a quarter for every dimension. So we'll come back to that later. Okay, so then of course the critical points, phi, so these are the critical points. So, as I said earlier, yesterday, x equals f of x comma theta. That's easy because you take the derivative in theta and then you find y must be equal to f of x. And then you have this map where you map those two. So now I have to add a covariable, and remember that there are 2 points, x and y, right? So x, and then I have to take the covector, take the derivative of the phase fraction in the x variable. So if I do that, I get theta, comma, and minus f dash of x, and then as a linear form, I put in a tangent vector, and the same in the y variable, so here with f of x, because of this. And then in the y variable, we have the identity map. So theta dot. And now you can see where the transpose comes in. So if you have to put it over there, that's the adjoint map, so to say. So that's equal to x comma psi comma f of x comma. So if you replace psi by minus psi, get the minus, where is it? Oh, there. Yeah. So get the minus here, and sorry, x comma f dash of x dual psi, and then f of x comma psi minus psi. Okay, so that's what you get, and this is what I claimed last time without the transpose, but now it's there. Okay, so now I feel better. But there is another warm-up that I want to do. So second warm-up, now that we've done the first, warm-up 2. And that's actually will be a useful one. So similarly, so we assume that we have a Fourier integral operator of a given phase function. And let's just for simplicity say that this is an Rn cross Rn, so n is equal to n twiddle. And it's given by some phase function, some relation coming from that phase function, and we pick a unit vector E in Rn. Doesn't have to be a unit vector, just some vector in Rn which is non-zero. And now define another kernel. Now I add an extra variable t, and I do it as follows: x comma y, and this is just k of x minus et comma y. So all I do is somehow shift the kernel in the x variable in the direction of E with a t, and I add that as an extra variable. Yeah, so then So let's write down in terms of this Fourier integral what this is. So this is 2 pi to the power minus 2n minus 2 capital N integral over r capital N. Then we have this representation e to the I phi x minus t e comma y comma theta, and a of x minus t e comma y comma theta d theta, right? So and when t is equal to 0, of course, that we get this representation as an ordinary Fourier integral operator, and a is this symbol of order, I wrote it down here, so I don't have to think, Sm plus 2n minus 2n divided by 4. Yeah? And so what's that as a Fourier integral operator? So that's again this representation. It's again a Fourier integral operator because it again has this representation. But what's the canonical relation? That's the question. So we have to compute this. So the critical points now, d phi t, this is of course just shifted critical points. This is t comma x comma y theta. So the theta derivative vanishes, of course. It's the same for the shifted version. So with the property that x minus t e comma y comma theta is in c phi. Now I have to map that using lambda phi t. And so what do I get? Goes the t, yes, t. So I get the t variable, and then t has a corresponding cotangent variable. Let's call it tau. So tau would be the t derivative of phi, right? But the t derivative of phi is the same as the x derivative of phi times e with a minus. So this is the x derivative of phi times e. Okay, so then we have x, then the x derivative of phi, y, and the y derivative of phi. Well, on, x, t comma x comma y comma theta must be, of course, in t phi t. So you just write down what this means. So you can also characterize it as follows. So that's just t tau, right? So let's give that a name. X comma xi comma y comma eta. And so this equation here just means that tau plus e times xi, so that's xi, right? That's minus xi, must be 0. And then we have x minus te comma xi comma y comma theta is in lambda phi. And that's the canonical relation if you shift. So you can see the thing just gets shifted, but you have this extra variable now that is useful to have. Yes? No, but I didn't shift it here. No, I think it's right. Okay, so what does it mean? So kt x comma y comma, so I think of t as an extra variable. So this is going to be because of this shift in dimension that I mentioned earlier, now it has a quarter order less on r cross rn with lambda phi t that was described here. Okay, so that's going to be useful later. Okay, so I think that's a nice warm-up. You can see I'm also appropriately dressed for doing work here. Let's get back to our spectral problem. So recall what we actually want to do. So I need to make sure that this is not erased. So if you see me erase that, you need to stop me. So what's our spectral problem? We have our globally hyperbolic stationary manifold. That's a long word, stationary. And I also want the Cauchy surface to be compact, so that's called space-like compact. So space-like compact spacetime. So that's going to be the generalization of a compact Riemannian manifold. And what this immediately means that you can actually write the metric globally as minus n squared as a product. So M is equal to R cross sigma, where sigma is a Riemannian manifold with metric H. And that's dt squared plus Hij dx j plus the wind Wx dt dx k plus Wk dt. So Wk is a vector field, it's called the wind. And you can see if you multiply this out, you get mixed terms of the form dxj dt times the covector hjk wj. Now, there is this representation, but it's not unique at all. So if you choose another Cauchy surface, it will look different. Why does it have that representation? Well, that's pretty well, it's not obvious, I don't know. So take a Cauchy surface, pick any, and then the flow lines of the Killing field are causal because of this condition that the Killing field is globally time-like. So they're causal, so that means that they intersect the Cauchy surface exactly at one point by global hyperbolicity. Okay, so that's how you get this factorization here. And that also shows you that there are 1,000 of, there are many, many more. Okay, anyway, so how do you even know W is a vector field? What's a vector field? Like this, yeah? So time independent, and H is a metric, which is also independent of T. So what's the Killing field here? That's d by dt. In this notation here. Once again, there are many, many such things, such ways to write that, but there are some objects that are invariantly defined. For example, you could take the norm of the length of the Killing field, and that you can see is, if you just compute that, it's not n squared because there are also these mixed terms. You get a dt squared here again, so with the minus. So the length of the Killing field is n squared minus w squared. What do I mean by w squared? W squared is just hww, so the length of this wind here. So that's, for example, a function that is invariantly defined on the quotient. So this is a smooth function. You can think of that as a smooth function on M mod R. That's an invariant object. So anybody, by the way, has a solution of what that first term in the while law would be? It's not going to be the volume of that. I can tell you as much. So I got one solution, which was, why don't you flow time 1 and take the volume of that slice that you get between two Cauchy surfaces? Right? Maybe that's not such a bad idea. But note that a conformal change, so if you multiply this by a constant, the spectrum doesn't change. But that thing changes. So whatever it is, it must be at least invariant under constant conformal changes of the metric. So that already gives you some clues, although I don't think that one can guess it so easily. Okay, so I need some more tools now. So we're going to do spectral theory, but let me just remind you of what we have on this space-time. So we have our operator box plus m squared, m is greater 0. And we have our retarded and advanced fundamental solutions, and we have the difference of these two. So this is going to be a distribution on m cross m. And distribution is in the kernel of P in both variables, in the x variable and in the y variable. So now let's do that thing that we did before. Let's add an extra variable. So define GS. What's that? It's also a distribution, but now this is going to be distribution. So excuse my notation, so it's clear what I mean. So I put variables there. That's a distribution that's not pointwise defined anyway. So I feel okay writing Sxy here. But that's now R cross M cross M. And how do you define that? Well, by GS x, y. And what you do is you flow in the direction of the Killing field. S, Z, X, Y. So you do that thing that I did here. And of course, there is a coordinate system in which the vector field is just one constant. So that means I can actually take that formula and I can conclude that whatever this is, it's a Fourier integral operator. So lemma. So this GS. Remember that G, that's Thematic, right? So that's a Fourier integral operator of order -3/2 with that canonical relation given by the geodesic flow. So because of this dimension ship, this is a Fourier integral operator of order -7/4 on some interval cross M cross M. So I'm not going to take all of R, but I take some interval minus epsilon epsilon, and under some conditions epsilon can also be infinite. So sometimes this is going to be actually global Fourier integral operator. Actually, I think it actually is a global Fourier integral operator anyway. No, I don't need this I. I is an interval, but I don't need it, so I'm gonna take this out again. I thought that I need it, but I need it for something else. So what's the canonical relation? Maybe I have more space there. So that's has been in the paper there was always a problem with getting it in one line. So okay, so we have S and then sigma, of course. So variable covariable, x psi, y eta. Well, you know where this is, so it's in T star R cross T star M cross T star M. And the condition is that it's just the same over there, but you can write it invariantly, so I'll bring this back now. So I guess it's here, right? So this is the thing we have to add. I don't know if I can do this in this line here. Okay. Okay, so sigma plus psi evaluated at the killing field Z, right? That must be 0. It's the same thing that's written over there in coordinates. And then, so it continues on the next line. E to the minus SZ x comma psi is equal to phi of t y comma eta for some t in R. So the one where S is equal to 0 is just the usual one that we had before, and I think I have to put a minus here to make it work, right? So always forget that. But yeah, that's the one from before. We have to flow here. That's the canonical relation. So there is no proof because it just follows from what's written there. That's the lemma. So how is that related to the spectrum? So maybe I should remind you about yesterday. So yesterday, we had a little definition, which means we defined the space H, the Hilbert space H. So what was that? That was the kernel of P, so the space of solutions of the Klein-Gordon equation. And we completed this in this quadratic form Q, but that's essentially, you know, some energy space. It's a Hilbert space. And so this Hilbert space is canonically isomorphic. So there is a restriction map which maps the solution to its Cauchy data. So this maps the Hilbert space to H, so H to H1 of sigma if you choose a Cauchy surface. So this is completely independent of the Cauchy surface. But if you choose a Cauchy surface, so maybe let's call it R sigma because it depends on the Cauchy surface, you get the initial data of the solution, right? So you have this restriction map here. And on this Hilbert space, we had a unitary operator with a one-parameter group, which implements the killing flow. So U of S is equal to E to the ISH. So U of S implements the killing flow. So what does it mean? It means that U of T is just e to the tz, but I restrict this to the kernel of p, well, to h, right? So I take my solution and I flow it. And, yeah, and so I get a one-parameter group that is strongly continuous on this Hilbert space. And so that has a self-adjoint generator that I call H. Why do I call it H? The Hamiltonian. And so we're now in the setting of self-adjoint operators on a Hilbert space. The only weird thing is that the Hilbert space does not consist of L2 functions somewhere. Some Hilbert space of solutions of the Klein-Gordon equation. Good, but we can describe nevertheless. So for what I want to do, I want temporarily make things dependent on the Cauchy surface and then go back and again make them independent of the Cauchy surface. So we were quite successful. It was a lot of fun as an exercise to add this extra variable. So I want to continue doing that now. But first, so we have this US, I think I called it, right? Equal to e to the sh, so I write it here again, times I. We define, similarly, I think of it as a distribution. I can smear it out with a test function, right? So what's that? So I integrate phi of s e to the I sh ds. So I just denote it like that. So this is also going to be an operator. So what's phi? Phi is a smooth compactly supported test function on R. I'm just using that as a notation. And similarly, I also define g phi in the same way. So that's a distribution, and I plug in the test function phi in the slot s from before. So that's as an integral. So please, every integral in this talk is a distributional pairing. Okay, I hope that's clear. I don't really use Lebesgue integration anymore. So gs, well, gs phi of s ds. Okay, so in other words, in the s variable, we pair this with the distribution phi, and we are left with two more slots. We get a distribution again. This is a distribution in d dash of m cross m. And yeah. Am I done here? No. Okay, so I have this unitary operator, but the Hilbert space is also isomorphic to this Cauchy data space. So I can actually use this R sigma to transport the unitary operator here. Let's do that for a moment. So let's define Vs equals R US R to the minus 1 sigma. For a moment. So this acts on H1 of sigma plus L2 of sigma. And I also define V phi, similar. Fine. So for a test function, I can smear this out. Okay, so now what's the kernel? So V phi doesn't have an integral kernel. Well, it acts on H1 plus L2. But in a sense, so V phi has integral kernel. I'll say in a second what I mean by this. R composed with G phi. Why is that? So R sigma composed with G phi. What's Vs? Vs is I solve my Cauchy problem, then I take the solution, I flow with it, and then I restrict to the Cauchy surface, right? But last time we saw that the Cauchy evolution operator is given by G. And so G solves the Cauchy problem. So this operator here, Vs has integral kernel R sigma Gs. That's maybe what I want to say, right? So how do I solve the Cauchy problem? Maybe I need to take the Cauchy data and think of it as a distribution on that is on M, supported on sigma. Do you remember that? Yeah. So you take the Cauchy data and you think of it as a delta distribution on the Cauchy surface, and then you take this Cauchy data and you think of it as a delta dash in the normal derivative. So I'm not going to write it down because it takes forever, but you remember that. Yeah? It was written down. So this is the rho star. So rho star thinks of the Cauchy data as a distribution on M with support on sigma. We have that. And then we take this G, we solve the Cauchy problem. So that's the solution operator of the Cauchy problem when S is 0. Now we flow with it. So we shift it by S. And then we restrict back to sigma. So can you see that this is just the same as Vs? Yeah. So the integral kernel is that. Now, the claim is, maybe I'm ready to prove something actually. Yeah, let's see. It was a kind of a walking proof, like where I just arrive at the result and I say we have proved. So I think that was the idea. Let's see. Okay, so the punchline is, it's going to turn out that G phi is actually smooth function. And it's going to work out for us because the only thing we need to do is to stare at this expression here. This one. So maybe I'll clean the board and you can stare at this expression. Huh? Oh, no, I'm okay. I used it already. Oh, thank you, but thanks very much for paying attention. Yeah, excellent. I don't need that either. So why is the wavefront set of this 0? So note, in order to show that this is actually a smooth kernel here, V phi as smooth kernel, integral kernel. Well, by inspection of this canonical relation. So because remember that Hermann criterion, it says, if we don't have 0 in the wavefront set here. If this is 0, then you cannot be in the wavefront set. Implies that it's a map from C, it's actually a kernel from C naught infinity to C infinity. Do you remember that? So now I'm thinking of this GS as an integral operator which maps C naught infinity functions. So I'm thinking of this as an integral, as an operator from functions on R to functions on M cross M for a moment, okay? So sigma equals 0 means psi must be equal, psi z must be equal to 0, but psi is light-like. Oh, I forgot to write that down actually. Ooh. Yeah, I forgot actually earlier. Psi is light-like, z is time-like, so it cannot be 0. And nobody stopped me. So where was this relation? It's already gone. I can't correct it anymore. So remember that this canonical relation actually was a bit more complicated than I said, because I forgot to add that psi has to be light-like and non-zero, right? And then it has to be related by this geodesic flow. I think I did it correctly the first time I said it, but now in the heat of the moment. Yeah. So psi is light-like, z is time-like, cannot be 0. So that's proving it. But it has smooth integral kernel, so the spectrum of V phi is the spectrum of V phi, so it's discrete. Why? Well, because it's a compact operator. But that's true for every phi. But what's V phi if you write it in terms of the operator? So that's e to the ith, right? Phi of t dt. And by spectral calculus, that's also the same as phi hat of h. Isn't that right? No, it's minus h. Phi hat of minus h. So now for any function, for any compactly supported function, so this is going to be a Schwarz function, which is analytic, but you have plenty of those, and you know that the spectrum is real, so you can make sure that your function picks up only certain parts of the spectrum. So my claim is that this is enough to show that H has discrete spectrum. Discrete spectrum. That's a bit quick, but you can see how this argument works. Yeah? You can see that I didn't actually use any operators, differential operators. I really only used the Fourier integral operator and G. And that philosophy will continue now. Yes? Yes, it does, yeah. Because yeah, sure. So for example, if you multiply the killing vector field by 2, then the spectrum will also get multiplied by 2. Yeah, that's right. So there is a trace formula for this. Actually, if you just take the trace of this, and you take the integral kernel of this operator, then you can compute the trace. So if it's a smoothing operator, note that we have to take the trace. It's a bit funny. It's the trace in H1, not the trace in L2, right? But all the eigenvalues, all the eigenfunctions are actually, so finite multiplicity, yeah? And all the eigenfunctions are smooth. So in particular, the eigenfunctions of H are smooth. So they're smooth functions, and means that they're all in H1 anyway. So the trace of this operator in H1 is the same as the trace of this operator in L2. Therefore, I can compute the trace by Mercer's theorem by just restricting the integral kernel to the diagonal and integrate over the Cauchy surface. So what do I get from this? I get the following trace formula. We obtain the following trace formula. The trace of u phi, which is the same as the trace of v phi, is equal to, and now I'm going to write down something that is independent of the Cauchy surface. So we take g phi, and then we take the normal derivative in the x variable, g phi x comma y, and we subtract the normal derivative of g phi of x comma y in the y variable. So that's some y distribution. And I'm going to restrict this to x equals y. No, I'm going to restrict it to y equals x, so that I can integrate over x over a Cauchy surface. So now, because g phi is actually a solution of the wave equation, remember that this gs, that was transported by a killing field. G solves the wave equation, but if you transport something by a killing field, the killing field commutes with the wave operator. So this solves the Klein-Gordon equation in the x and in the y variable. And remember, there is this integration by parts argument, which says if you have that, then this expression is actually, after restricting it to the diagonal, after restricting it, not before, after you restrict this expression to the diagonal, this is actually, this defines, well, it's a divergence-free vector field. It's an integral over a divergence-free vector field. So this is actually independent of the Cauchy surface. Do you see that? I don't know. I guess the computation is the same that you do when you have u of x in u of y, or v of y, minus v of x in u of y. Right, so that's not, of course, independent of the Cauchy surface, but if you restrict it to x equals y, then you integrate it. We've seen that this is just a symplectic form. So this is basically the symplectic form that you get if you take smooth functions and you identify them with the tensor product of smooth functions. So is it clear now why this? I mean, I can also compute it. It's actually not a very difficult computation. Maybe I'll try. I'll use my luck here with computations on the board. So let's just do g phi of x comma y. So we take the differential in the x variable and minus the differential in the y variable, and then restrict to y equals x. And the claim is this is co-closed, right? So take delta of y, or delta of x of this. So what I get is delta d in the x variable, but that's 0. And I have used Leibniz rule here because I restrict afterwards. So I get delta x dx, so delta y dy in the y variable here. It's also 0. For the wave equation, it's 0. For the Klein-Gordon equation, every term produces an m squared. So after restriction to the diagonal, it cancels out again. Yeah. So this is a simple. If you didn't see it now, please do it as an exercise. So this is completely independent of the Cauchy surface. So if you wanted, you can formulate it algebraically. So there is a way. This defines a cohomology class, or maybe I should have explained this a bit better. So the way this has to be understood is minus dy. So g phi of x comma y. So now that's a smooth function, right? So you get this one form, and then you restrict this to y equals x. So you get a one form on M, which is co-closed, and you apply the Hodge-star on M. And now you get an n minus 1 form, and if you integrate this over the Cauchy surface, that's actually the same as the expression that I wrote down with the normal derivatives. That's what I used here. I'm sorry, maybe that's not completely obvious. So I'm just really bad at Green's formulas. That's why I do it this way. But it's really just Green's formula. So this is a perfectly valid trace formula now. And this is going to be the foundation of, so everything that you want about the spectrum is encoded in this G phi, which is therefore just, G, essentially the distribution GS. This wave trace, and this is therefore a distribution by some, Fourier integral operator, yoga, on how a trace of US is in D dash, and here is my minus epsilon plus epsilon. So it exists as a distribution if you avoid, so we have to look at this canonical relation here. Now you want to restrict this. Well, how do you do this trace, right? You smear this out in this S variable, and then you restrict to x equals y. So as a distribution, you should think of that as you restrict to x equals y, and then you integrate out the x variables. This is the trace. And so in this way, you can use symbol calculus and the canonical relation to see where the singularities are. And so what's the singularities? It's because, no, sorry. But it's actually a Fourier integral operator, that's what I was going to say. And then you have these clean intersection conditions that I didn't want to explain. Yeah, thanks, you're right, of course it's on the whole interval. But we're going to focus on the interval from minus epsilon to plus epsilon. So it turns out that the singular support of this, so we want to understand where the singular support of this is, yeah? And so that's simple calculus, and I don't have time to explain, but unfortunately I also erased the relation from before. So the relation was this, right? Where? There that's exactly what I need, yeah. So, sorry? Yeah, psi light-like, yeah. I can edit here, fantastic. Like, and non-zero. So I have this light-like size, and so they lie on a time-like curve. So if I want to come back to the same point, so x comma psi, I need to come back to the same point y equals eta. For this to be, I take the trace, right? I want x equals y. And after integration, it turns out that what I need to be in the singular support is also y equals psi. So the only way this can happen is I get back to from x psi to y eta with these two things. Yeah? So in the Riemannian case, this means, well, they have to lie on the same geodesic. That's the usual Poisson relation. So here it means something else. It means that you have a null geodesic, and this entire null geodesic is mapped to itself by the Killing flow. Okay, so what's the singular support of this distribution? It has a singularity at 0, and then all the other singularities are at the times when the Killing flow maps a light-like geodesic to itself. Maybe I don't have a lot of time, but maybe I should draw a picture. So suppose we do this on a circle, right? Or a cylinder like this, like sigma times r. What happens in this case? So what are the light-like geodesics? These are exactly geodesics like that are actually geodesics on here, but I lift them with the S parameter to the product. Okay, so null geodesic correspond to geodesics on the base that I lift uniquely. So a null geodesic, so they look like this. And then the killing flow goes up here. So you see what happens is after some time, I might actually come back to the original geodesic. On the base, that corresponds to a closed geodesic. But that's only true in the product case. In the stationary case, it's more complicated. It's exactly what I wrote. It's, well, I didn't write, but I said. You consider the space of null geodesics, and you consider the set of closed orbits, and the singularities of this distribution must be there. So we can analyze this now. That's what we did. But I promised you a while law, so I want to actually shorten this a little bit now and get the while law done. Find it. Okay, what's the while law? It's really strange. Here's what you get. So you get a singularity at s equals 0, and you have to analyze this singularity. And if there is a bit of time, I'll explain to you how this is done. Maybe I'll explain it now, because it needs a little bit of motivation, maybe. So the trace of us, u phi, is just the same as the integral over e to the it. Well, didn't we already say this? So this is the same as trace of phi hat of h, right? So in other words, that's the sum over all phi hat of lambda j, where lambda j run over all the eigenvalues of this h. So now what you want to use for phi hat, so phi hat, what you want to use is a function like this. Yeah, so that's the counting function. That counts how many eigenvalues are there. You really want to use that one, actually, but you can't use that one because that's not smooth and its Fourier transform is not compactly supported, okay? So you can actually change this function a little bit. So then you have a little wiggles here to make the Fourier transform compactly supported. You get a compactly supported Fourier transform on this side here. So this is phi, or inverse Fourier transform. So you can do these wiggles, and the wiggles don't really contribute, so they have a little O error, which we don't care about for this moment. I'll just want to sketch the argument. So now what you want to understand Weil's law is you make this, you scale this up, and so this gets blown up like that, right? What happens on the inverse Fourier side is this compactly supported distribution goes up like this. And so it's clear that the leading term of the singularity at 0 of this distribution here is the thing that gives you the Weil law. So all we need to do is to analyze this singularity at 0. And now remember the Hadamard expansion that we did long ago? This actually gives you, you can use the Hadamard expansion. You can use the Hadamard expansion. Yeah, let's go back to the Hadamard expansion. So to actually compute this here, because it's given in terms of Riesz distributions, so you do the Riesz distributions, you compute this stuff, and you can get the first order term. So let me tell you what the result is. So you can do this computation, and if I have time, I'll do it. But the leading term is not so difficult. That's not how we did in the paper, by the way. In the paper, we used honest Fourier integral operators, and you get actually a slightly different result. You get a different result, I'll show you, which is actually the same result, but it looks completely different. Maybe I already alluded to this. So what you get, let me tell you first what gets out of this symbol computation, which, by the way, was very painful. So let's define the eigenfunction. It depends on the killing field. That's correct. Good point. So that's the number of eigenvalues from 0 to lambda. You can also do from minus lambda to lambda. The spectrum is symmetric anyway, because you can complex conjugate the solution, and then you get a negative spectral point. Okay, so lambda j, eigenvalues of h. And now what you can do is you can so you just take the space of scaled null geodesics. Null geodesics. By this, I mean future directed ones. What's scaled here? Scaled means that they still come with a parameter. I don't forget about the parameter. So they still have a speed, okay? They're parameterized. So this, of course, if I choose a Cauchy surface, then this becomes canonically isomorphic to the cotangent space of this Cauchy surface, okay? Now the cotangent space of the Cauchy surface has a symplectic structure. Let's take that and move it over here. So this is a symplectic space, okay? So it turns out that it actually doesn't depend on the Cauchy surface. It's always the same symplectic space. So the space of scaled null geodesics, so that was known before, is actually a symplectic manifold. So it has a volume form on it. Let's take that volume form. So if you have a scaled null geodesics, you can take its derivative and pair it with the killing field. So you get a function on n. Let's define the function n z smaller equals 1. What's that? So that's a subset of n, and it's the set of all gamma with the property that gamma dot z equals smaller equals 1. Maybe I need a modulus, by the way. Do I? No, they are future directed, so this is going to be positive anyway. So this is some kind of ellipsoid in the cotangent. In the way, if you do the computation, this is an ellipsoid in this cotangent space. So it turns out that you can actually compute this. So this is actually the volume of this with respect to the symplectic form. So everything is invariantly defined. Yeah? If you can compute it, Z is equal to the volume of the n-1 dimensional unit ball times the integral over the Cauchy surface n of x, so n is this thing from before, times n squared minus w squared to the minus n over 2 times integrated with respect to the h volume form on sigma. You can check now that this is actually a conformal invariant. Constant. If you use constants to rescale G, then this doesn't change. And this is going to be the term in the Weil law, so theorem. And that's also what you get from the Hadamard expansion. You get this. So the Weil law says nz of lambda is equal to 1 over 2, well, okay, some constant depending on the dimension, I don't want to write down, times the volume of n z smaller equal 1 times lambda to the power n-1. So note the jump of the n is the space-time dimension, plus little o. Oh, actually, it's much better than the n-2. So that's what you get if you make this rigorous here using Fourier-Tauberian arguments. So this means that this integral, whatever it is, does not depend on the choice of Cauchy surface. I don't know if that's completely obvious. It's also it's not only an invariant, it's a spectral invariant of the stationary space-time. I already mentioned the Poisson relation. I think I can explain this a little bit more now. What about the other singularities? Not the one at 0, so they also give you stuff. They also give you spectral invariants. In fact, I think they are important because I expect them for black holes to give contributions to the scattering matrix in the sense of the Biermann-Krein formula. Okay, nobody has proved the Biermann-Krein formula for Schwarzschild as far as I know, but so these things so these closed orbits that I mentioned before, they correspond to this photon sphere. So you expect the contribution from the wave traces in this way. What's the singularity at it's not t equals 0, but at other t's? Ooh. So the computation with the Hadamard coefficients, by the way, that's not published, but I'm in the process of finalizing this. Because you can also compute the second coefficient. Maybe I'll give you that first. There is a second coefficient. And it corresponds so that you can do this. Now you have the spectrum. You can compute heat traces and theta functions. But as you know, there is the first coefficient, which is the Weil term, and then there is a second coefficient, which is usually the integral over the scalar curvature. Right? So you wonder what is it here, and it's a complete nightmare. So second term I actually announced this already, but I think there was a term missing. Well, no, well, in the modified while law, yeah. Well, so you can so if you keep those wiggles here, then you can actually get a full asymptotic expansion. The second term, but you can also do, what you can also do is lambda jt, and you sum that over all the lambda j's that are greater equal 0, and you also get an asymptotic expansion. And then the first term again is the while term, and the second term, that's the term I'm talking about now. No, there is a no, I don't think so. I think it's the same as for closed manifolds. I mean, yes, so that's right. That we also proved. Yes, so of course you have just the same actually. No, so no, I don't know. I mean, yes, in general you wouldn't expect to have a second term. But there is never a second term. I don't know. I mean, so if they have measure 0 in n, right, the set of closed orbits, then you have the little o. So I mean, it's the whole thing is. Yeah, it's the same. Yeah, it's the same. Yeah, I know if you have a boundary. So the same you expect here. If you introduce a boundary here, then yeah. No. I mean, you have to mollify, but I mean, the second terms, they are spectral invariants, right? So they are just the higher wave trace invariants. So for example, so there is, maybe it's not completely obvious. So there is a yoga that relates poles of the zeta function to coefficients of the heat trace to coefficients of the wave trace. So it basically just Fourier transform, Mellin transform, Poisson transform, this direction, that direction. But once you compute the second term, you have computed all the other second terms as well. So I'm just giving you the second term because I don't have time to say all this. But so the second term is proportional to the scalar. So depending on what you're looking at, the second term, whatever it is proportional to, because the constant depends on what you're doing. But you would expect something like the scalar curvature. And so it's 1 over 4 times 6, what's that? 24, right? Times the scalar curvature. Good. That's the same as in the Riemannian case, right? But that's the scalar curvature on the space-time. Okay, times n of x, right? Times modulus of z to the power minus n plus 2. What's modulus of z? Remember, that's just n squared minus w squared. So that's the norm of the killing field with minus g of z, comma z. So I'm just writing it like this because it's shorter. Okay, unfortunately, that's not all, so there is more. Minus n minus 2 divided by 6n. So you can see how one can make a mistake here, right? Ricci z, comma z, well, that's also an invariant, right? Modulus z to the minus n. That's not it. Minus n times n minus 2 divided by 48 times n of x times g of the covariant derivative of the killing field of itself, with itself, and the norm of that, times modulus of z minus n minus 2. That's not it. You could like, well, how many expressions are invariant that you can write down? Okay, plenty, it turns out. Plus 1 over 12. And here is another one, which is problematic. So unit normal vector field, very strange. Z, modulus of z, minus n plus 2, plus n minus 2 divided by 12, modulus of z, minus n g of the second covariant derivative of the killing field with respect to itself, times the normal vector. Now, my collaborator complained bitterly about these two terms. For good reason, because they don't look invariant. They depend on the normal field, and therefore they look as if they depend on the killing field. Turns out that if you integrate this thing over a Cauchy surface, it does not. And that is, for me, it was very difficult, and it's actually several pages of computation using the Pogozaev-Schön identity. Yeah. I mean, maybe there is an easier way, but yeah, that's the unit normal to the Cauchy surface. So what you have to do is you take this thing and you integrate it over the Cauchy surface. It turns out that the second term here is invariant. The others are actually invariant. So n times the volume form actually corresponds to the volume on the quotient, for example. So this is unpublished here. As I said, I'm working on it. And I'll just finish here by saying that closed orbits of the killing flow, e to the tz, on the space of null geodesics, but this time I don't care about the parameterization, okay? I really take the null geodesic. So closed orbits on the space of projective null geodesics contribute singularities of the form so 2 times the real part, 1 over 2 pi I e to the I pi over 2. There is some kind of Maslov index here that one can define, times the gamma, closed orbits gamma. Gamma is the periodic orbit on this np. So it turns out that you can define the return time, the simple return time. So maybe for people who don't know the Thematic trace formula, this doesn't make a lot of sense. But you can ask me afterwards. So there's a Poincare map, which is also associated with this flow, because that's a quotient of a symplectic space. So you can think of it as the time one, sorry, the energy one surface. Forgot something. So T minus T gamma plus I0 to the minus 1. So depending on this Maslov index, you sometimes get delta distribution, sometimes you get something else. Okay? So you can see that this is completely analogous to the Thematic trace formula. So this is under the assumption that the orbits are non-degenerate and simple. So these are spectral invariants then for stationary space-time, and you can see the whole thing generalizes. In fact, I think I'll start. Oh no, actually I have still 4 minutes, right? Didn't I start later? This one here? Sorry, where? Yeah. Oh yeah. So I said this before. So I should maybe explain it a bit better, because of course I said it in words. But if you're into this and you've thought about it, it's easier. But I was actually very confused about it myself. So if you have an null geodesic, right, like this, you can take a parameterized version. And if you take then the tangent here, if it's parameterized, it has a length, or it corresponds to a vector or covector, and you can project this down here, and you get an element in T star sigma. Okay? But if you parameterize it in a different way, you scale it, then it gets scaled here, right? So if you take just a null geodesic, it corresponds to an array here in T star sigma, not to an element in T star sigma. So you have the projective null geodesics correspond only to rays. So in fact, the space of projective null geodesics is the space of null geodesics divided by the scaling, namely by R+. So and N is then the symplectic vector space, and NP is the quotient of this vector space by the R action. So you have a homogeneous, what is it called, a conic, there is a name, I forget. Yeah, you flow on N, and you also flow on NP, right? And of course there are infinitely many closed orbits on N, because if you have one on you just rescale the geodesics, so there is a whole family. Yeah, so the wavefront set is also conic, so you can see that in this homogeneous picture. Yeah, so there is also a semi-classical version of that we wrote, but it's more complicated. When you let the mass go to infinity at the same time as you increase the energy, so this is like an asymptotic thing. You can also let the mass go to infinity. In this case, you don't only get light-like geodesics, but time-like geodesics in a similar picture. That's another paper. I don't really have time. Maybe that's already good enough. Okay, I think I'll stop here. And if there are any questions.